Okay, so deflection of BC. So PBC is 4 times 10 to the power 3 minus by 32.791 times 10 to the power 3, because Q over here on BC is acting on what? Pressure. Okay, then divide by the cross-sectional area, which is 2.827 times 10 to the power minus 3. Young's modulus is 70 times 10 to the power 9. And then the length is 0.5. Okay. So 4 power 3 minus by 72, 4 power 3 minus 32.791 power 3 times 0.5 divided by 2.827 power minus 3 divided by 70 power 9. So the actual motion is equal to minus 72.745 times 10 to power minus 6 meter. Okay, minus means it's going to shorten. Okay, it's going to go into what? Compression. Okay, so if we were to come back to the actual problem, it's still compression. Okay, so if we were to just turn it the other way around, hold on. If we just turn it the other way around, okay, if we just turn it the other way around, right? Compression means what? It's going to be negative, right? Compression means acting downwards. So point B will be acting towards the reference. Okay, so the negative down here is where the compression is. Okay, so you can see after the hangman, everything is easy. Yes or no? Right? After the hangman, everything is easy. How do I get 10.107? Where's the 10.107? Oh yeah, yeah, correct. Chen Xiang. Thank you. Okay. Okay. So the most important thing about this method, okay, I've just shown you, is when you divide into the section, what force to use. Okay, that is the critical part. And also a reminder that tension is positive, compression is negative. Okay, that's why I picked this problem for that reason only. Okay, right. So from here, I'll let you guys finish copying first. Okay, my bad. Okay. Then we're going to do another example. Okay. The next example I'm going to do is it's a combination of static and elastic deformation. Okay, I repeat again, it's a combination of static and elastic deformation. Okay. And also beam analysis. Okay. Oh, yeah, I think for this case, because I'm looking it from the upside down view, let's cancel off the up or down. Okay, you'll get confused. But we know that Q will be acting in compression in BC. Okay, we know that it's going to be a compression BC. Okay, anyone, any questions so far? Okay, I don't hear anything. By the way, the next example, we will go up to 12, 10, 12, 15, okay? If you have to go, you have to go. It's all recorded, okay? But example number 2 is important. Okay, sorry, I should not say that if you have to go, you have to go, okay? What about the 2.56 times 10 to the power minus 9? This is, you multiply just considering this. Okay, ignoring the 4 times 10 to the power 3. Start off, okay? Okay. So let's look at example number 2. Let's look at example number 2. As I said, example number 2. Now this is a PO question. Okay, the professional exam question where you have a problem like this. Okay, is these all going to be posted? Yeah, they're all going to be posted on Avenue to Learn. I post everything. I don't care. Okay. Okay. So you can see a rigid bar. Okay, and I like to draw your attention to the word a rigid bar. ABC is supported by a 20 millimeter diameter pin at point A and two 12 millimeter diameter cable at point B and point C. So we know that the two diameter of the cable, they are 12 millimeters. Okay, they are 12 millimeters. And a cable at point B is 4 meters long, and a cable at point C is 2 meters long. Both cables are made of steel with a U strength. Interesting, yeah? They only give you the U strength of 400 megapascal, right? And the elastic modulus of 200 gigapascal. So now on your mind, right? You know why that they only give you what am I? Now in your mind, you know why they only give you the U strength, not the ultimate strength. You don't need the ultimate strength for this anymore, right? You don't need the ultimate strength. And the elastic modulus is 200 gigabyte. The bar is loaded with a triangular distributed load, okay, of 20 kilonewton, the maximum. 2/3 out of the bar, plus a concentrated load of 25 kilonewton acting at the top of the bar at point C. So the one with the most marks is part A. We have to determine the forces developed in each cable. And part B is find the horizontal displacement at the top of the bar, which is at point C. I'm going to ignore part C, okay, because you should have learned single or double shear. I'll teach double shear later on when we're doing shearing stress. Okay. So as I said, I picked this problem because it has a lot of layers. Okay, it has a lot of topics combined together. One is static, the other static analysis, elastic deformation, and also on distributed. Now, some of you say, Eugene, we have not seen this type of loading before, right? So the structure is both loaded in a triangular load and also a point load. Okay, so let's first of all, let's construct the free body diagram. Okay, let's construct the free body diagram. So I'm going to focus more on the diagram first. Okay, so we are going to construct, I'm going to call this integrated free body diagram. Okay, why I use the word integrated? Because it's going to be a multi-body. Okay, Right. So before I go on, okay, I'd like to explain, okay, this term over here. Okay, what does rigid body means? Okay, what does rigid body means? Right, you can see the term, right? ABC is assumed to be rigid body. So it means that during deformation or during loading, right, member ABC will be a straight line or point A, point B, and point C share the same gradient. Okay. Now, until probably week 9, okay, where we are more advanced, then we're not going to assume as rigid body. Making a rigid body assumption is just to simplify our analysis. Okay. So what do we mean by that? Okay, I'm going to do some side work at this end. Okay, so if we have a structure now, okay, and this structure is built in, or it's not necessarily built in. Okay, it's on a pin. Right, what am I doing? Okay, and you have point A. Somewhere around here is your point B, and over here is your point C. And you have a load down here as in your AX, and then you have another load down here as in your BX, okay, based on this transformation. So this is X and this is Y. And we are going to make the assumption that AX is greater than BX. Okay. So when the structure is deformed, when we assume that ABC, okay, is a rigid body, or ABC, yeah, ABC is a rigid body. During deformation, the structure will deform this way. Okay, the structure will deform this way. It is a straight line because we assume a rigid body. So down here will be our A prime, a new position. Down here will be our B prime, a new position. And down here will be our C prime. So that's what we mean by the deformation will be a straight line or, okay, point A or A prime, B prime, and C prime share the same gradient. Okay, they share the same gradient. That is what we mean by rigid body. It is just to make our analysis simple. Okay. In the real world, okay, what will happen? In the real world, probably you have something like this. Okay, it's just a sketch. Okay, in the real world, you probably have a deformation that looks something like that. It's just a sketch, as I say. So we assume it to be a straight line. Okay, we make life easy for ourselves. Okay. Right. Okay. Any question? What do you mean by rigid now?